Good day, students. We are considering a very important topic in an AC circuit, which tells us how current and voltage they move, whether they are in phase or they are out of phase. Sometimes currents always lead the voltage. Sometimes voltage always leads the current. When the circuit contains only a resistance R, they are in phase. Both voltage and current, they are in phase. They move at the same time, at the same pace, at the same steps, and also they are in phase. What do I mean by that? I root mean square. I equals I naught sine omega t, and also V root mean square equals to V naught sine omega t. Current moves at the same in the same phase with the voltage because it contains only resistance R. But under when circuit contains only a capacitance, current moves out in 90 degree ahead of the voltage. What do you mean by that? You can see from a circuit containing only resistance R, the AC voltage vibrates in phase when it steps with the alternating current. Thus, the phase angle between the voltage and the current is zero. If V equals V naught sine omega t, I equals I naught sine omega t, and this theta equals omega t, that's phase angle. And for a circuit containing only a capacitance C, theory shows that VC and IC are out of phase by an angle 90 degree. Good. Now, the current IC leads on the voltage VC by 90 degree. This means that the angle by which a particular phase of IC is in advance of a similar phase in VC is 90 degree, or pi over 2 radians. Pi is 180 divided by 2, give you the 90 degree, or 1 over 4 circle. 360 degree make a circle. When you divide, you still have 90 degree. In consideration of time, IC, that is current, capacitive current, gets to its maximum, minimum, or zero value ahead of VC. VC, that's voltage in the capacitor. And also, if VC equals V naught sine omega t, then IC equals I naught sine omega t plus pi over 2. It means that current leads the voltage under the circuit that contains only a capacitance. See, in circuit with primarily capacitive load, current leads the voltage. Why? Because the two plates of the capacitor has charges. The current has to move to those two plates before voltage comes into play. What I say, this is true because current must first flow to the two plates of the capacitor where charge is stored. Charge is stored at the two plates of the capacitor. Current must first flow there. Only after charge accumulates at the plates of the capacitor is a voltage difference established. The third case is if only an inductor L is connected to an AC voltage. Theory shows that current IL lags on the voltage VL. In this case, voltage leads the current because the inductor acts some charges, energy storage in the magnetic field of the inductor, which creates voltage within the magnetic coil. Now makes the voltage to be generated before the current. Okay, now let's see. IL lags on the voltage VL by pi over 2 radians, means that the interval of an angle or time by which a specific phase of VL is delayed with respect to the phase of IL is pi over 2. This induced voltage leads the current by 90 degree in an ideal inductor. When it involves only an inductor, voltage leads the current, but when it involves a capacitor, current leads the voltage. Now, this phase shift is a result of the energy storage in the magnetic field of the inductor, and it causes the voltage to reach its peak before the current does in each cycle of an AC waveform. Now, I is I naught sine omega t, V because of V naught sine omega t plus pi over 2. This is what makes voltage to lead the current because of the energy storage in the magnetic field of the inductor. In a circuit containing RLC, the current is the same for all the components of the circuit and is in phase with the voltage across R. Now, this is the tan phase angle, VL minus VC over VR, because VL is IXL and VC is IXC over IR, equals I. Bring the I out, I cancel I. To me, this formula is very important as inductive reactance and capacitive reactance over R. Now, if XL is greater than XC, phi is positive. When you subtract it, to give you positive value when XL is greater than XC, and I lags the voltage. I lags the voltage under inductor. That is, voltage leads the current. Now, if XL is less than XC, automatically the value will be less. If the value is lesser than the second one, it will be negative, and current leads the voltage. Means that XC is greater than XL capacitor, and the current that reads 90. The phase angle is 90 degrees because the current leads the voltage. That's what makes it to be negative. For resistors and inductor in series, what made it to be series? The current that is coming from AC source. Current moves and there is no division. As current enters resistor, it comes to the inductor. That means that there is series. V voltage that comes from the AC source is equal to VR squared plus VL squared, R, which is Ohm's law. Now you now have I squared R squared plus I squared, because you are squaring it, each of them, XL squared. Now find the square root inside, because I is common, you bring it out, these two cancel the square root. V equals, find the square root of I squared, factorize R squared plus XL squared. Is that okay? This, you cancel this, I will now come out. We now remain square root for this. We now have V equals I, we now come out because it has cancelled its own, remain R squared plus XL squared. Now I equals, divide both sides by square root of R squared plus XL squared. R squared plus X as inductive reactance. This cancel this. Now therefore I equals V over square root of R squared plus XL squared. XL squared. Don't forget there's an expression for XL. XL equals 2 pi FL. Don't forget. Now, when you come to this current under inductor and resistor, our current lags on current I lags on the applied voltage V by phi. How do you know that it lags? Current lags. When you see the arrow going up, means that voltage is leading the current. Where the arrow is pointing to means that it's leading, while the one that doesn't have an arrow is lagging. And tan phi, because it involves inductor and resistor, it will be VL over VR. The VR will always be at the denominator, VL will be at the numerator. Now VL is IXL, that is, when you apply the Ohm's law, IR, instead of using R, you will use IXL over IR. I cancel I. You now have tan phi. This angle because XL over R. When you see a question like you have to look for this for, they will give you frequency and inductor, divide by the resistor, you get your tan phi. Now phi phase angle, so the tan inverse of XL over R. This is the formula to use to get phase angle. phase angle equals to phi. Take note. The last expression for the inductor, we have I equals V over square root of R squared plus XL squared. The impedance, we use that to represent impedance equals square root of R squared plus XL squared, but involve only resistor and inductor. Now let's for R and C, resistor and the capacitor in series. You have the source, so to represent AC source, goes to the resistor and the capacitor. The line will be the same. Now when you have that, what is going? The arrow. Now the voltage here to VR and also VC. Now V, that is moving, voltage, its current is moving like this, because VR plus, they are in series, VC. Now you have V equals to I, using Ohm's law, IR squared plus IXC, everything is squared. Now, sorry, V squared, V squared, V squared, V squared. Now you have to square it because like you are doing Pythagoras theorem, V is source is equal to D squared plus D squared. Now you have V squared equals I squared R squared plus I squared XC squared. V squared equals, factorize out, I squared to R squared plus XC squared. C squared. Factorize out. We have both have R squared plus XC squared by R squared plus XC squared. This will cancel this. Now half I squared equals to square root, sorry, I now equal square root of V squared over R squared plus XC squared, and separate them equals to square root of V squared over square root of R squared plus XC squared. These two cancel this. We have I equals V over square root of R squared plus XC squared. In this case, we have the capacitor, capacitive reactance to be 1 over 2 pi FC. It's 1 over, but under inductor, capacitive inductive reactance, we have 2 pi FL. Current I leads on the voltage by phi. In this case, we draw R, current will be here, voltage will be here. Mean that current R is facing the current, that's current leads the voltage of phi. And don't forget, you can say V lags the current. Look, in this case we are talking about leads the voltage, because the current moves to the two places of the capacitor before it starts generating the voltage. That means that current comes before the voltage. In that case, you have tan phi equals VC over VR. So that voltage across the resistor will be down. It's always down, which is IXC over IR. I cancel I because of XC over R. And your phase angle equals to tan inverse of XC over R. And when we are talking about when it involves R, L, and C in series. It's similar to what you have been doing. And now have you see, you have the resistor, you have the inductor, we have the capacitor. The voltage is coming. This R, this L, and this is the VL, VR, and VC. This is the voltage. Now have V squared that's coming to V R squared plus open bracket, because this one is constant. When you open the bracket, you have VR squared plus IXL minus IXC squared. Now you have V squared equals I squared R squared equals, you can factorize I out, plus I squared XL minus XC squared, because I squared squared upon. Now you can now bring them out. V squared equals I squared into R squared plus open bracket XL minus XC squared. Find the square root of both sides. Have it that this square will cancel these two. This square will cancel this. The remaining square root inside this. Now P equals I square root of R squared plus XL minus XC squared. You have P equals I square root of R squared plus XL minus XC squared. Divide both sides by that. Square root of R squared plus XL minus XC squared over square root of R squared plus XL minus XC squared. Now this cancel this. Therefore, your I current is moved with the RSC circuit equals to square R squared plus XL minus XC squared. And where Z impedance equals square root of R squared plus bracket XL minus XC squared. It's an impedance. You can replace it over there. And when you have to look for the phase angle under this, phase angle tan phi equals VL minus VC over VR. That's the phase angle. In case you are not giving the voltage direct, that's expression for this as IXL minus IXC over IR. Current is common. I open bracket VL bracket XC XL minus XC over IR. I cancel I. Now the tan of the phase angle equals XL minus XC over R. Phase angle equals to tan inverse of XL minus XC over R. This is the end of our class. Have a nice day.